Hello everybody. On this video, I'm going to talk about some technique called something called source conversion, and which is going to be a very handy tool technique in solving the network problem and finding the equivalent circuit in many problems that you will see. So source conversion technique simply says any voltage source with a series resistance, right, is something like non-ideal voltage source, is equivalent to a current source uh, with the same series resistance in parallel with that current source. That would provide the same load current if you connect a load. So that, let's say this is a series resistor and this is the same series resistor, and this current is given by this voltage. Let's say this is V in, so whatever voltage source you have divided by this series resistance. So this circuit is similar to that circuit. That's what the source conversion says, and we're going to prove it. So we're going to prove it both analytically and numerically. So let's do that. So to prove this, so first connect a load. This is a load resistor, right? Any load resistor, right? And so let's say in this picture it gets the current, let's say IL. So IL is the load current. So IL from this circuit, what is I of L? The load current is going to be just, this is because this series resistor and load resistor are in series, so the load current is just going to be V in divided by R series resistor plus RL. And then we're gonna just do a little bit of rearrangement. So I can do this, right? I can just divide and multiply by the series resistor, and the denominator you still have the total resistance. Now what is this? V in divided by RS is some current, right? Let's replace that way, which is V in divided by, which is this current source, divided RS divided by RS plus RL, right? And so now I can say that load current is given by RS divided by RS plus RL times the total current, right? Which is nothing, just the current divider in the load, right? Current divider circuit. This is nothing, this is nothing, it's just the current divider circuit, which would supply the same load current, right? IL by the right. So that's why we can prove that, we can analytically prove that this circuit, which is simply a voltage source with a series resistor in series, is exactly equivalent to a current source with a same series resistor in parallel, and both should deliver the same current on the load resistor if you connect a load resistor, right? This is equivalent to that, and this circuit is going to be very useful in source conversion, is going to be very useful in network solving problem, and also quick finding the equivalent circuit. So that's analytically, right? That's analytical proof. And let's put some number. Let's prove it with numbers as well. So I'm going to erase this real quick, and then I'm gonna now, let's prove it by putting some numbers, right? Let's use some numbers and solve the actual problem to prove the source conversion is true. So in both cases, let's say this is figure number 1, figure number 2. For figure number 1, what is the load current? So load current, let's put some, so let's make this load resistance, let's say 10 ohms, just some random number. So load current using the voltage source in series with 20 ohms is going to be so 10 volts divided by 20 plus 10, right? So that's 1/3, right? And that's 333 milliamp of current, right? Okay. Now from the second circuit, let's prove this. The current through the load resistor is going to be same or not. So to do that, you can either do Kirchhoff's voltage law or current law, right? So I'm just going to do nodal analysis. So let's make this a ground reference voltage. So then what you need to find is just this node. So let's call this is at the voltage on this node is V. Okay, now let's see if the second circuit, which is the current source equivalent of this, delivers the same load current or not. And it's very easy to do that. So let's say I'm just going to use a nodal analysis, or you can use any analysis. So let's say I'm grounding this, making this reference voltage, and let's say this is the unknown nodal voltage V. So we just need to figure out this one unknown nodal voltage V to find the load current, right? So at V, right? At V, I is going to be I of S. So I'm calling this the series current, right? So the series resistor plus the load current. But I is, so based on the source conversion, this source, voltage source with the series resistor is equivalent to a current source, which is equivalent to that voltage divided by the series resistance. So that is 10 divided by 20, which is half amp. So I of S is that unknown battery voltage, unknown nodal voltage divided by the series resistor plus again this divided by the load resistor, which all these numbers are given. So this is half, and this is V divided by 20 plus V divided by 10. So let's simplify that. Is V plus 2V, right, is half, so that's going to give me 10 is equal to 3V. So V is going to be 10 over 3, which is 3.33 volts. Now you can find the load resistor, load current. Load current is just from this circuit. The load resistor is getting V, so load current is whatever that nodal voltage we just found divided by the load resistor, which is 10 ohms. So 3.33 divided by 10 ohms, which is 0.33 amps. So you can, we just proved that, right? In both equivalent circuits are delivering exactly same load current, 0.33 amps and 0.33 amps, 330 milliamps of current. So then we just proved that this circuit is equivalent to that circuit.